15 Hudson Yards is a super tall mixed-use tower built on the western edge of Manhattan, above a working rail yard. This building is not just a typical skyscraper, but a structure completed with precise engineering atop a complex urban infrastructure. In this video, we will follow the entire construction process of 15 Hudson Yards, how it dug into the ground, raised its walls, and lifted its core as it grew toward the sky. The western edge of Manhattan, where 15 Hudson Yards is located, was once land reclaimed from the Hudson River. As a result, near the surface, there is a layer of urban fill containing construction debris and various remnants. Beneath that lies an alluvial layer composed of soft clay and silt, and deeper still is increasingly dense schist. Such soft ground lacks sufficient self-supporting capacity, making it highly susceptible to collapse or settlement during deep excavation. Furthermore, the area's proximity to the Hudson River results in a very high groundwater level, and active railroad tracks still run beneath the site. If groundwater were to infiltrate or vibrations occurred during excavation, it could have a critical consequence for the railway system. Under these complex conditions, a structure were needed that could both stabilize the excavation and completely block groundwater. For this reason, the slurry wall method was essential at this site. Slurry wall construction involves creating a strong underground wall that both blocks water and supports the soil. This method is generally carried out in following steps. The first step is installation of a guide wall. This guides the exact location of the slurry wall and helps ensure the excavation equipment operates vertically and stably. Once the guide wall is in place, full-scale trench excavation begins. Using specialized equipment, a deep trench is dug while simultaneously injecting bentonite slurry to prevent the trench walls from collapsing. When excavation is complete, massive steel reinforcement cages are slowly lowered into the trench. These cages are a core structural element that ensures the strength of the eventual concrete wall. Next is the concrete pour. Concrete is injected from the bottom of the trench using tremie pipes, displacing the lighter bentonite slurry upwards as it forms the wall from bottom to the top. The slurry in the trench is removed using a pump, and soil particles mixed in the slurry are separated through the descending process. Construction proceeds in a panel segments of fixed lengths, using an alternating sequence where some sections are completed first and others are filled in later. This strategy improves ground stability and ensures structural continuity. Each panel is connected to adjacent panels using joint tubes, and the reinforcement cages are tied together to form a continuous wall. Once the slurry wall is complete, the soil inside is excavated in stages. Instead of removing all soil at once, a ramp is created to allow step-by-step excavation. This is done so that large excavation machinery or casing equipment can later move freely from ground level to underground. While the overall slurry wall process progressed as described, one major issue emerged. That was the difference in excavation depth between 15 Hudson Yards and the shed. This was due to the differing number of basement levels for each building, with 15 Hudson Yards requiring deeper excavation. As a result, there was a risk that relatively shallow soil on the shed side might collapse toward the deeper side of 15 Hudson Yards. To prevent this, the construction team installed an additional slurry wall along the boundary between the two buildings. This slurry wall served both as a retaining structure and a cutoff wall, acting as a physical barrier to separate ground influence between the buildings. The foundation of 15 Hudson Yards employed the caisson method to reliably support the immense loads of super tall structure. Caissons are large diameter pile structures that reach down to the solid bedrock, directly transferring the building's weight to the deep ground. The construction process begins with excavation at the designated locations using a pile drilling rig. During excavation, a steel casing is inserted to prevent ground collapse and groundwater intrusions. After drilling is completed, a surging operation is performed to remove slime from the bottom of the excavation, followed by measurement of the drilling depth. Based on the measured depth, the rebar cage is fabricated. The circular rebar cage assembly yard is typically set up near the ground reinforcement piles. Once the rebar cage is completed, it is lifted and transported by a service crane, then carefully lowered into the drilled hole. After the large prefabricated rebar cage is inserted into the hole, concrete is poured from the bottom up using a tremie pipe. Once the concrete is fully placed, the caisson becomes a pile foundation directly anchored into the firm bearing stratum. After the concrete has cured completely, the casing is removed. These caissons are then tied into the upper pile caps and the mat slab, distributing the building's overall structural load safely and evenly. The foundation system of 50 nuts and yards consists of pile caps installed atop caissons and a massive mat slab that covers them. These two components are not merely stacked vertically, but had to be meticulously integrated using rebar and concrete. When installing the pile caps on top of the caissons, the rebar is designed to extend sufficiently upward. After placing the rebar for the pile cap, additional rebar is placed for the stop column that will sit above the pile cap. This overlapping of rebar ensures smooth stress transfer between the two structural elements. Next, formwork for the pile cap is installed, and concrete is poured. Then formwork is also installed for the stop column, and concrete is poured accordingly. Afterward, a high-density rebar mesh is laid across the entire mat slab, and the pile cap, stop column, and the mat slab are cast together as a single structural unit. In this way, the pile cap, stop column, and mat slab function as an integrated foundation system through strong rebar anchorage and flawless concrete placement. This is why even the slightest error cannot be tolerated in the construction of a super tall structure. The fixed structure of the shed began construction before 50 nuts and yards. In the latter half of 2015, after the foundation platform was completed, the superstructure of the shed itself began rising. The construction process for each floor followed these steps. First, a steel frame composed of columns and beams was erected. Next, metal deck plates were installed on the top of the steel beams. These deck plates served as formwork during concrete pouring, and once the concrete cured, they became structurally integrated with the steel to form a composite slab enhancing overall stiffness. Concrete was then poured over the deck plates to create the structural floor slab. Finally, concrete was poured into the formwork of the steel column frame to complete one floor of the shed. The following describes the construction of one floor at 50 nuts and yards. The lower level construction of 50 nuts and yards was a high difficulty project due to its structural integration with the previously built shed. In particular, the lower levels featured K-shaped incline structures, an irregular exterior form, and a trailing core method, where the outer structural frame rose before the core, requiring a construction strategy from typical high-rise concrete buildings. After the lower floor has sufficiently cured, rebar is placed for the exterior columns, beams, and slab, while reinforcement work for the core walls is carried out simultaneously. In the trailing core method, the core rises after than the outer structure, making the logistics of material delivery and the sequencing of work even more critical. Next, formwork is installed for the exterior columns, beams, and slab. The formwork is constructed on shoring towers, and for the K-shaped incline structures, specialized slope formwork, bracing, and anchoring systems are applied. At the structural boundary where 50 nuts and yards meet the shed, a separation joint was installed to allow each building to move independently. In this area, dowel bars were pre-installed to allow slight horizontal movement while preventing vertical displacement. The dowel bars were installed in the previously constructed slab for the shed, with sleeve caps covering half of the cylindrical elements to absorb horizontal movement relative to the adjoining structure. These details play a crucial role in preventing cracks or stress concentration at the slab connection caused by thermal expansion and contraction. Concrete is then poured simultaneously into the outer structural frame and the core. The top surface of the slab is finished smoothly, and thorough curing is carried out using methods such as water spraying, covering, and application of curing compounds. Finally, after confirming the concrete strength through specimen testing, all formwork was dismantled. After that, individual formwork systems are lifted, and surveying and construction preparation for the next floor began. Through all these procedures, the lower structure of 50 Knudsen yards was realized with high engineering precision, overcoming structural complexity, interference from adjacent buildings, and spatial constraints. The mid to upper floors of 50 Knudsen yards no longer require structural coordination with the shed, allowing for more streamlined construction process and maximized efficiency. From this point onward, a full-fledged 3-day cycle method was implemented, with each floor constructed through a precise and repeatable routine: formwork installation, rebar placement, concrete pouring and curing, and formwork removal. The key element that enabled this rapid construction pace was the climbing form system. This system reused the same formwork for the repetitive exterior wall sections and elevated it to the next level using hydraulic jacks after each concrete pour has cured. It reduced dependence on cranes and greatly enhanced efficiency during repetitive floor construction. On the first day, after the lower floor has sufficiently cured, rebar is placed for the exterior structure and core walls, and MEP piping and electrical wiring are installed at this stage as well. Next, formwork is installed for the exterior columns, beams, and slab. On the second day, concrete was poured simultaneously into the outer structure and core, with vibratory compaction, ensuring the removal of internal air pockets and achieving structural integrity. On the third day, after verifying concrete strength through specimen testing, all formwork was removed and climbing form was raised to the next level using hydraulic lifting system. Surveying and layout marking followed to prepare for construction of the next floor. Thanks to this systematic and repetitive process, 15 Knudsen yards was able to complete its upper structure rapidly and reliably, achieving both a shortened construction timeline and highly efficient project management. As a super tall structure, 50 Knudsen yards required a lateral load resisting system capable of withstanding wind and seismic forces. The key structural element fulfilling this role was the outrigger system. The outrigger construction followed these steps. First, I-shaped outrigger steel members were anchored and embedded into the concrete of the mega columns. Then, K-shaped steel columns were connected to the I members, and the first of the two segmented outrigger struts was attached to the K-shaped columns. The second segmented strut was structurally connected to the top chord and delay joint, which had been pre-embedded within the core wall. Finally, the bottom chord of the outrigger was connected to the K-shaped steel column, completing the full outrigger assembly. Every components are first connected with bolted joints. Once deformation due to self-weight occurs and the structure stabilizes, they're then welded together. This precisely executed outrigger system significantly enhanced the structural stability and stiffness of 50 Knudsen yards, enabling it to withstand strong lateral winds blowing in from the Hudson River. As mentioned, 50 Knudsen yards utilized a trailing core construction method. In this approach, the core rises later than the outer structural frame, making it impossible to transfer concrete vertically through the core as in conventional methods. For this challenge, the construction team installed a dedicated concrete pump tower. The concrete pump tower is an independent structure built inside the building, designed to vertically pump concrete from the basement to the upper levels using high-pressure pumps. The concrete pump tower was assembled and installed at ground level after foundation work was completed and the structural frame for 1 or 2 ground-level floors had risen. At 50 Knudsen yards, ready-mix concrete trucks and concrete pump truck entered the underground space located beneath the high line. The concrete was loaded into the pump truck and continuously delivered to the upper levels of the building through the piping system connected to the concrete placing boom. At the upper structure, a concrete placing boom was installed. It rotates and extends its boom arms to distribute concrete freely across the desired pouring areas. As construction progressed, the pump tower was lifted floor by floor, rising in sync with the building in an integrated manner. Thanks to this system, the core's delayed construction did not interfere with construction placement, and consistent quality and speed were maintained for stable concrete delivery to the upper floors. In the construction of a super tall building, the tower crane is one of the most critical pieces of equipment. At 50 nuts and yards, the tower crane was installed between the two cores after the completion of all foundation work. However, once the entire structure is complete, safely dismantling this massive piece of equipment becomes a separate, highly complex procedure. At 50 nuts and yards, the tower crane was installed using a self-climbing internal system, and its dismantling followed a precise planned, multi-stage process. The dismantling was carried out in reverse order of the assembly. First, the crane's horizontal jib and counterweights were removed. This was done safely using the crane's own hoisting mechanism, or an auxiliary crane. Next, the operator's cab and slewing unit was dismantled, and the crane's mast was gradually lowered section by section by reversing the action of the hydraulic climbing mechanism. Once the crane reached the minimum height it could dismantle itself from, a derrick crane or a small mobile crane was assembled on the roof to lift and lower the remaining components one by one. The dismantled parts were then transferred to the ground via the building's elevator shaft or an external hoist. The final derrick crane itself was disassembled into small enough modules that workers could manually bring them down to the ground level. In the case of 50 nuts and yards, the area around the core slab where the tower crane was installed had been structurally reinforced from the design stage to withstand the loads generated during dismantling, and comprehensive safety measures were planned to account for winds, vibrations, and impact throughout the process. The crane dismantling marked the final step in completing the structure and represented the culmination of precision and planning in high-rise construction. 15 Hudson Yards is not just a typical super tall building. From the slurry wall deep beneath the ground to the dismantling of the tower crane high in the sky, this structure is the culmination of countless technologies, processes, and the relentless precision of human hands. Despite complex ground conditions, the constraints of being built above active rail lines, the structural coordination with the shed, and the challenges of a trailing core system and a high-rise concrete construction, this building now stands firmly as a defining feature of the Manhattan skyline. The construction story of 50 nuts and yards you've just watched is proof of the moment when technology creates space and space transforms the city. Next week, we'll cover the overall discussions. Thank you.